Welcome to day 26 of 50 days of tutelage. In today's class, I'll be teaching you about gravitation. And the first thing I would like to address is the general misconception that people have about gravity in general. People always assume that whenever you hear gravity or gravitation, it definitely means that, oh, if you have the ground, the level ground like this, and you have an object that is above the ground at a certain height, and that object will surely fall down. And this falling down is what gravity is. They often say whatever goes up must surely come down. And they think that this is what gravity is about. Actually, that is not what gravity is about. In the simplest term, gravity is all about attraction. Gravity is all about attraction. So when we talk about the concept of gravity, we're talking about a force. When we talk about gravity, we're talking about a force, and Newton was able to help us define what this force is. And it tells us that gravity is a force of attraction that exists between any 2 point masses. So once a body possesses mass, so let's say you have body 1 which possesses mass, let's say that one is m1, you have another body, a body 2 which possesses mass m2, and they are at a certain distance apart. Let's call that distance r. Then there is a force of attraction between these two objects, and that force of attraction is known as force of gravity. So that's the first thing you need to know. And then so Newton was able to state that this force of attraction is actually proportional to the product of those two masses, which implies that depending on how massive the bodies are, that is also how strong the force of attraction between them is going to be as well. So if you have bigger masses, you have higher force of attraction, greater force of attraction. And then if you have smaller masses, you have lesser force of attraction. But it did not stop there. You can have big masses, but a distance apart as well. It depends on how close or how far you are from each other as well. So it is inversely proportional. This force of attraction is inversely proportional to the square of their distance apart. Meaning that if somebody is at a very long distance, like two masses, if they are at long distance from each other, then their force of attraction is going to reduce. So the farther you are away from someone, then the lower the force of attraction between the person and you. Or in this case, generally any mass object, any object that has mass in the universe. And that's basically the general concept about gravity. So gravity is not about what goes up will surely come down. No, that's not the case. However, we now have, so where does the concept of what goes up comes down, where does this concept really come from? I'm going to explain everything bit after bit, and I'm also going to explain that it's not every time that whatever goes up would come down. So in this video, I'm going to be explaining about the concept of escape velocity. So make sure you get your notes and you stay glued throughout. Another thing you should also do is that you should subscribe to my channel, like this video, and then comment as well. And thank you. Anyways, let's move on with the class. So now I want to talk about the gravitational field strength. Gravitational field strength. Now, at different points, we tend to define something called gravitational field strength. Gravitational field strength. And at a point in the universe, if you want to define gravitational field strength, it is defined as the gravitational force per unit mass. So when you begin to measure force per unit mass, then you are talking about acceleration due to gravity. Acceleration due to gravity. So acceleration due to gravity is actually another name for gravitational field strength at a point. So gravitational field strength at a point is defined as the gravitational force per unit mass acting on a small mass that is placed at that point. So that is basically what that is talking about. So if you have a body now, and then let's say this is the earth, and this body is here at this point. So what happened here is that there is a kind of strength. So this earth has its gravitational field. And what is a field? A field is a region of space where the effect of a force can be felt. So there's a field in this region around the earth. And then this body that is around the earth now can feel the impact of this. So the impact, the strength, what this is feeling at this point is the acceleration due to gravity. So that is why it can fall down at a certain rate. And that rate at which it is falling down is g, which is force per unit mass. Force per unit mass. So therefore, in this situation, when I defined earlier that F is proportional to m1, m2, and then is inverse proportional to the square of r. So therefore, we can redefine F by using an equation, and we introduce the G, the big G, which is the gravitational constant. This is known as the gravitational constant. Now, do not get it twisted. This G is acceleration due to gravity. This G is the gravitational constant. So you have gm1 m2 divided by r squared. So if I decide to now say acceleration due to gravity, which is F divided by m, that is the point mass that is in question. So in this case now, if the two bodies I'm talking about now, I'm talking about Earth, let's call that one big M. I'm talking about this other mass here, let's call that one small m. So in that situation, if I bring these two together now, I will have that F equals G multiplied by big M multiplied by small m divided by r squared. So if I put that here, that will be G multiplied by m multiplied by small m, then r squared divided by, so divided by m will also mean multiplied by 1 over m. And from there, you can see that this small m will cancel out. So therefore, the gravitational field strength, which is also known as G, for any planet or for any place on Earth or in the universe is given as the gravitational constant big G multiplied by the mass of that particular place divided by the square of their radius. So in the case of Earth now, this will be the mass of Earth. This will be the mass of Earth, and this will be the radius of Earth as well. So what does that imply? It implies that there are some other planets as well, and there are some other bodies in the universe that also have their own G. They also have their own field strength, and which is also known as the acceleration due to gravity on those different bodies in the universe. So you can always replace this mass with such mass of that body, and you can replace this R with the radius of that body. So that is the general concept about G. The next thing I want to talk about is gravitational potential. I'm going to give you the definition, and I will explain everything about the definition one after the other. So gravitational potential is always defined at a point. So if I say, what is the gravitational potential at this point? The definition says that it is the work done per unit mass. It is the work done per unit mass. Per unit mass in bringing a small test mass. That is, I'm bringing this particular mass now. I'm bringing this mass from infinity to this point. So the work I will do per unit mass to bring this mass from infinity to this point is known as the gravitational potential, and it is always represented using the letter V. So let me break the definition down one after the other. What do we mean by work done? First of all, work done is force times distance. From what you already understand, I already explained this thing earlier in the previous class. Work done is force times distance. But it says work done per unit mass. In that situation, that implies that this is not just ordinary work done. It's kind of saying that if this is the entire mass that you want to bring from infinity to that point, then if, let's say, this mass is of 20 units, the work done we are requiring here, the work done that is being talked about here, is actually the work done that is going to be used for just 1 unit. That is why it says work done per unit mass. So therefore, naturally, if the work that you will do to remove this 20, let's say for instance, if you buy 20 pieces of a certain item, let's say you buy it for $200, then that is the work done. That is the amount that you will use to buy these 20 pieces. So if you want to calculate how much you will use to buy one, what do you have to do? You have to divide it by what? By 20. So therefore, this work done is not just ordinary work done. It's work done per unit mass. So therefore, this is going to be divided by the mass. So work done per unit mass in bringing a test mass from infinity to that point. Now, here's the thing. I'm also going to explain another thing here. such that this V is always going to take a negative sign. And why is it so? You see, the infinity is a reference point, and in this case is a point where we have zero potential. So at infinity, infinity is a point of zero potential. However, infinity relative to the Earth, though Earth should be spherical. By the way, whatever I'm doing for the Earth, it also applies for every other place in the universe. I'm just using Earth as because it is easier for me to reference. So infinity relative to the Earth is more like you're going far away, far away, far away from the Earth. So therefore, if we say infinity is at this, let's say at this point now, and is a point of zero potential, and you want to do a work in bringing this object, you're bringing it somewhere around the Earth like this now. That implies that you are doing a work and you are falling below the zero potential level. So therefore, this point below zero will be negative. Of course, I can use integral and some advanced math to explain better, but I don't want to bore you with all of that. So it is not a point above infinity. Above infinity will be positive because you're now doing work into the whole thing. But this time around, when you are doing a negative work in this system, when you are bringing it from infinity, which is a point of zero potential, to a point near the Earth's surface. So therefore, this potential now, Fd over m, is going to be negative F over m multiplied by d. D is the distance. Since I've been using r, so I'm just going to replace it with r now. But if you remember very well, this F over m is actually our acceleration due to gravity, which we have discussed earlier, which is the field strength. Now, in that case, you now have negative g times r. So this is your potential. Now, let me use capital V. It is your potential, gravitational potential. And you also remember that G was defined to be negative Gm divided by r squared. So if you multiply this by r, what you're going to get is your gravitational potential is negative Gm divided by r. By the way, I want you to pay attention to all these things, especially the r, because I will say something about it later. R in this case is definitely the distance from the center of the Earth to that object itself. Oftentimes, it is approximately the radius of the Earth, but there are cases whereby it's not approximately the radius of the Earth. I will explain that very soon. So, transitioning from gravitational potential, let's now talk about gravitational potential energy. They are actually similar, gravitational potential and gravitational potential energy. They follow the same definition. The only difference now is that you will remove this part that says per unit mass. So is the work done in bringing the actual mass from infinity to that point. So gravitational potential energy at a point is the work done in bringing the actual mass to that point. And that is why in this case now, all you have to do is to multiply your gravitational potential by the mass, and that will give you gravitational potential energy. So in this case, you have negative Gm m divided by r. And if you look at this very well, this looks like, if I keep this mass, let's say this is mass, this Gm over r is actually the acceleration due to gravity multiplied by r. I mean, based on what I did here earlier, if you actually do that, Vm is going to be, so what's V? Negative Gr times what? Times m. I know it looks like a mgh, but I'm going to explain that much later. So that is what gravitational potential energy is. So I believe it should be able to differentiate between gravitational potential and gravitational potential energy. So let's proceed. The next thing I want to talk about now is for satellites. Some satellites are actually in orbit around the Earth. Like I said, this can be any other place as well. I'm just going to be using Earth as a reference point. So around the Earth. Now, there is a distance between this satellite and this Earth. Let's call that distance r, as we have been saying it. So this, as they are moving around the Earth, they are moving around the Earth, they are moving in a circular path. And the radius of that path is this r. So therefore, we look for a way for them to stay in orbit. But the force that is responsible for keeping them in orbit is a centripetal force. And this centripetal force is simply the force of attraction between this guy and this guy. So therefore, that force of attraction we have already explained earlier, that will be F equals mass of the Earth multiplied by the mass of the satellite divided by what? R squared. But at the same time, we also have that This guy possesses centripetal force. So this force that is holding it to the center of that circular path is the one also responsible for its centripetal force. So therefore, the centripetal force is going to be mv squared divided by r. So in that situation, the m can cancel out and we can solve for the velocity with which this satellite is orbiting that planet. So we have v squared divided by r equals m divided by r squared. Of course, there is a g here. Sorry about that. I forgot this. Now, there's a g here. And then, so if you do that, that implies that v squared. Now, this v now is not your potential. V is velocity now. The orbital velocity of the satellite. V squared is going to be gm multiplied by r over r squared. And that implies that this is going to be gm divided by r. Hence, this is going to be v equals square root of gm over r. Now, when we're considering objects that are very, very close to Earth and we're considering a radius that is approximately that of the Earth, so this escape velocity is going to be, the orbital velocity rather, is going to be gm divided by the radius of the Earth. If it is not the Earth we are talking about, then you can also use it for any other one that you're talking about. However, there are some objects that they are above the surface of the Earth at a certain height. Let's say this is at a certain height, h above the Earth. So everything that I've used r for earlier, so r now becomes r plus h. So which implies that if the satellite or if any object is at a certain height above the ground and then the distance between the center of mass of the object and the Earth is not approximately radius of the Earth, that is, there is a significant height above the ground, then we use this r plus h. H being the height and r being the radius. So therefore, for instance, now acceleration due to gravity, that was gm divided by r squared or gm divided by r squared earlier. In this situation now, we have g will now be gm divided by r plus h squared. That is, if you are told that it is at a certain height above the Earth's surface, at a certain height above the Earth's surface. And this same thing applies for every other thing here that I've explained earlier. If it is not specified that it is at a certain height above the Earth's surface, just go ahead and use the radius of the Earth. But if it is specified, then you have to sum the radius of the Earth and the height that it is above the Earth's surface. You have to sum it together before you use it in any of the calculation. And the next one is what we call escape velocity. So I've already explained earlier that we have what we call work done from infinity and then you bring it to a certain potential. So there is escape velocity. And what is escape velocity? If somebody wants to escape this influence of the Earth's gravitational field, like the statement that people usually make that whatever goes up comes down. Like I said from the beginning of this whole class, that is not always the case. It is not every time that whatever goes up comes down. And in the case of this escape velocity, that is what we are going to be saying now. If somebody is projected with enough velocity such that is able to make it away from the influence of Earth's gravitational field, then that thing that goes up is not coming down again. So therefore, how do we define that? So the first thing is that we use the law of conservation of energy. When you project this object, it has two things. It has kinetic energy and it has gravitational potential energy. But when we want it to escape to infinity, a point of zero potential. At this point, total energy in this place is equal to zero. And total mechanical energy from the initial point is kinetic energy plus potential energy. And so what is kinetic energy? That's half mv squared plus gravitational potential energy that I gave you earlier. Gravitational potential energy, which is V, is given as negative gm m over r. That's negative g m over r. So what do we have here? Everything will be equal to zero due to law of conservation of energy. Total energy from the point of launch, which is the sum of these two, equals zero, which is the total energy at infinity. That infinity is like the point where this body already escapes the influence of the gravitational field. So therefore, you can now solve this. You have half mv squared equals, so you take that to the other side, you have gmm over r, And then this m can cancel out. Then you have v squared equals 2gm divided by r. That implies that v will be square root of 2gm over r. So therefore, here you go. The same thing I said about r, always pay attention to it here. You can see that it has a similarity with that packing velocity, because packing velocity is just square root of gm over r without the what? Without the 2. So what's the relationship between them now? So you can say that v, which is escape velocity, and this is orbital velocity. Escape velocity is square root of 2 multiplied by that of orbital velocity. So take note of that relationship between the two of them. So we've been able to talk about most of the things that you need to understand about gravitation. Of course, there are so many other things that you could also know about this, but I'm going to limit this particular class at that so that I don't give you too much. So don't forget, you should subscribe, you should like, you should comment as well. I'll see you in the next one.